Example 16.7. In this example, we consider a steady heat transfer between two large parallel plates which are maintained at constant temperature of 300 Kelvin and 200 Kelvin respectively. These two plates have a distance of 1 centimeter from each other. Assuming that the surfaces are black, therefore the emissivity is equal to 1, we need to determine the rate of heat transfer between the plates per unit surface area, assuming that the gap between them is, and we have 4 choices. The first one is filled with atmospheric air. The second one, the section is evacuated. The third one is a section is filled with urethane insulation. And lastly, is filled with a super insulation, which has an apparent thermal conductivity of 2 times 10 to the negative 5th watts per meter Kelvin. For this problem, we are going to neglect the convection taking place between the two plates. Therefore, the two only modes of heat transfer that we're going to evaluate are going to be radiation and conduction. Okay, so for conduction, we're going to simply say that it's going to be equal to the thermal conductivity of the fluid, the area, T1 minus T2, divided by the distance in between. For radiation, on the other hand, we said that is going to be equal to epsilon, sigma, the area, T1 to the 4th minus T2 to the 4th. Okay, so we're going to start evaluating each one of them. So we're going to start with case A. For case A, it says that it's filled with air. So for conduction, we need to find the value of K for that particular, for this particular condition. So we go to the book and notice that we have a temperature of 300 on one side and 200 on the other one. So the temperature that we're going to use is going to be the average temperature, which is going to be 250 K. And that is the temperature that we're going to use to find the properties. So we go to the back of the book and we find that the value of K for air is equal to 0.0219 watts mK. And since we're over here in the book, we're going to find also for part C the value of the K for urethane, which is 0.026 watts mK. Okay, so now we're ready to calculate the values of the conduction. So for part A, and notice what we're looking for in our case is Q dot divided by area. So the area is not given, so we have Q conduction as a function of area. So for part A, the value of air is 0.0219 watts mK. And the difference between temperatures is going to be 300 minus 200 Kelvin. And the distance in between is going to be 1 centimeter, so it's 0.01 meter. Therefore, the value that we have for conduction and divided by the area for part A is equal to 219 watts m squared. Okay, so that's the total value for conduction for part A. So for part A, we also have radiation. So Q radiation, function of area, is going to be epsilon. The value of epsilon was given to be 1. The value of sigma, the Stefan-Boltzmann constant, is 567 times 10 to the negative 8 watt m squared Kelvin to the 4th. And the two temperatures that we have are going to be 300 to the 4th minus 200 to the 4th. And this is once again in kelvins to the 4th. So we see that this becomes 369 watts m squared. So for case A, we see that the total value is going to be the addition of these two quantities. Therefore, the total value, Q total for part A, is going to be equal to 588 watts m squared. So now let's go to part B. So for part B, it says that the space between the two plates is evacuated. What it means in terms of heat transfer is that the amount of conduction that you're going to have is equal to 0. Remember, conduction requires a medium. Therefore, it is not going to be able to have any conduction. Therefore, the only component that you're going to have for this part is going to be radiation. And for part 2, the total value is going to be equal to the 369 watts m square. For part C, the space between the plates is filled with urethane insulation, and we already have the value of the thermal conductivity, so we could find that for C. The value of conduction per unit area is going to be equal to 0.026 watts mk, and this is going to be 300 minus 200 Kelvin, and the distance is 0.01 meter. Therefore, the quantity that we have over here is going to be equal to 260 watts m square. Now for this part, what we assume is that the material is very opaque, therefore it will be able to block the radiation waves that go from one plate to the other one. And what that means is that for this particular case, we have that the radiation component is going to be equal to 0. And once again, because the type of insulation that it has, it does not allow the radiation waves to move from one side to the other, and therefore the only component that we're going to have in this part is going to be equal to the 260 watts m square, which come only from conduction. Now let's do case D. Once again, in this case, we have a super insulation that takes place, so we're going to have a certain amount of conduction, and that is going to be equal, notice that the value that it has is 2e to the negative 5 watts mk. This is once again 300 minus 200, and the distance in between is 0.01 meter. The value of the conduction taking place in this case is only 0.2 watts. Once again, because this is an insulation material, the assumption is that it's opaque, and therefore the radiation value that you're going to have for this particular case is going to be 0. And the reason is that the waves are not allowed to travel from one location to the next, and therefore the total amount of heat rate is going to be equal to 0.2 watts. This is a summary of the 4 results that we obtained in this problem. Notice that the highest amount of heat transfer rate that takes place is going to be when the space between the plates is air. The lowest that you're going to have is going to be 0.2. So let's see if we are designing windows. Ideally, we want to be able to see through those windows. So using insulation might not be the best possibility because it's not clear and you cannot see through those. However, if you have a door, that would be a good choice. If you had the choice for a window, you will rather use vacuum rather than a space that's simply air in the space, because it has a lower heat lost in between the two surfaces.